last week we talked about equilibrium on a rigid body. Now I mentioned that starting from chapters 3 and 4, everything will be just the same material, but just building it up a little by little, okay? So when we talked about equilibrium of a rigid body, we mentioned that we draw free body diagrams for entire bodies, right? Not just for points. So this week we're going to start an analysis that looks at entire bodies, but simplifies its calculations to points. So we're going back to equilibrium of a particle. This chapter is called Structural Analysis. And if you read the title of the chapter, you may be thinking, wait a minute, this sounds a little bit too advanced for an introductory statics class. And it does sound advanced, but it's actually not that complicated. Structural analysis just means that we're going to look at structures. And what is structures? Well, if a particle is a point that has mass but no size, and a body is a collection of particles that give us mass and size, a structure will be a collection of bodies that gives us, well, what we call a structure. So when we think of structural analysis, what we're saying is that we're analyzing multiple bodies that are connected to each other and whose forces affect each other. Now what that means is that we can't really study these individual bodies in a vacuum. We always need to consider the reactions and the forces that their connecting bodies exert on them. So we're going to start our analysis on our study on structural analysis by studying trusses. Has anybody ever heard that word before? Trusses or truss? What is that?
I've heard it before. I don't remember what it is.
What about you?
It's like a support for something, so you can.
Like some sort of support, right? And that's essentially what trusses are. Like I said, I'm not gonna use my artistic lack of ability to show you what a truss is. Just you can Google it. But essentially, trusses are connections of members, okay, that help support a structure. You may have seen them, for example, in cranes, right? You have these very, very big, very, very long cranes. They have these little triangular shapes. Those are trusses. You may have seen them in the support of roofs, particularly if you have wooden structures, right? You'll see that the roofs actually have these triangular shapes. Those are trusses. And the reason we use trusses is because they allow us to distribute the force in such a way, right, that a smaller number of elements can withstand a larger amount of force. So we will start this week's study by analyzing trusses. And we're going to start with a simple truss system. Now, I was thinking before we started the class on whether we should start with theory or just go straight to a problem. I think I would like to go straight into a problem because we already know the theory. It's equilibrium of a particle, its moments, its equilibrium of a rigid body. Now I would like to apply that theory into the study of a truss. So let's say that we have the following structure. Okay, so the following collection of rigid bodies. We're going to have a truss connected to a hinge. Before I keep drawing, right now, the truss is connected to the hinge. In which direction can this truss move if it's connected to a hinge? A truss is just a bar right now, a bar that will form part of the structure. But in which direction can it move?
Only about the axis.
Only about the hinge, right? So it cannot move linearly in any direction, but it can rotate about the hinge. So right now, that's what we're dealing with. And then
Only on one axis, right?
Yeah, just this axis, about this axis. And now let's say that this truss is connected to another truss. Now what does this tell me? Well, the connections between trusses will be treated as if they were hinges. In other words, those connections, right, will prevent any relative movement in any linear direction, but don't necessarily have to prevent rotation between them. Okay? So when we look at two trusses connected, you can assume that that connection will be a hinge. Let's say, and this was actually my bad, but let's say that instead of a hinge, the truss is actually in a roller. And now, let's say that this truss is connected to a hinge. Looking at this system, where we have a structure that consists of two trusses supported by a hinge and a roller, what movement is possible right now? Just looking at the system the way it is. Remember, we treat these connections as if they were hinges, okay? And remember that hinges really only prevent rotation. So what we have here is a hinge, sort of, but on a roller, so they can also move linearly. So right now, what movement is allowed or is possible in this system?
It would flatten.
Exactly, it can flatten, or if you apply a force in this direction, it can, whatever the opposite of flatten is, right? Unflatten. That doesn't sound right. It sounds right, it just doesn't sound right for this scenario, okay? So, I will add two more trusses connected to each other as well as to the supports. Let's pretend that these are straight lines. So all the trusses have the same dimensions, okay? Not the same dimensions, but the same widths, okay? I'm just not drawing straight lines today. And I'm going to add one more truss right here. So we have our trusses. I'm going to write this one the top one. We have our trusses that are connected to each other, and remember that those connections, we will treat them as hinges. And then the trusses themselves are connected to a hinge and a roller, which means that free rotation, but not free translation, and then free translation and rotation, but no translation in the vertical direction. So this is what we call a simple truss system, or a simple truss structure. Conceptually, if we look at this structure, again, considering that these connections are like hinges, in which direction, if any, is movement possible to them?
Right, you can move in any direction, because if you move out, if you roll out from the left, right, the other hinges would stop, it wouldn't go out, and you can't really close in either.
That's correct. Let me adjust the camera here. That's correct. So it looks like the way this system is designed, there shouldn't be any movement possible. I mean, technically you could take the whole thing and rotate it about this hinge if you push upwards, but no relative movement between the trusses. Okay, so now what we're going to do is we're going to analyze this system in order to find all the forces acting on this truss. So in order to find those forces, I must first consider some external force or some body force. I can consider gravity, but let's not consider gravity. In fact, whenever we study trusses, because we have so many different systems, so many different elements, rigid bodies, then we're not really going to consider gravity for each of them. So for now, let's take gravity to be negligible. But let's say that I apply a force of 450 pounds to the top truss. Okay? So I apply a force of 450 pounds to the top truss, and I'm going to give you some dimensions. Let's say that this truss system is 4 feet in height and then 8 feet in width. So that's what we have. I'm applying a force of 450 pounds on the top truss. And then for simplicity, I'm going to identify my joints as A, B, C, and D. I said a new word there. What's a new word? Identify. You've never? No. Joints. I'm glad. It's funny how more than one person said identify. We're going to look at our joints, okay? And when I say joints, what I mean is the connections between the trusses, okay? And when I say identify, what I mean, no, you know what identify means, okay? So what I want now is to find the forces acting on each of these trusses. Now, these trusses are rigid bodies. If I apply a force of 450 pounds, just think conceptually, what forces can these elements experience? Well, because they are rigid bodies, and notice that this force will either push or pull some of them based on these hinges, the only forces that they will experience are going to be either tension or compression. Is that correct? So we're not really going to consider any shear force, right? Any bending forces, but we will try to find the tension and the compression that each truss experiences. Now, just for a general, I would say, conceptual view, do you think this is enough information to find every single force acting on each individual truss, or do you think we need more information? Sorry? But I can find those with this information. So I'm saying based on what I've given you. So if I give you this, could you solve and find the forces on each and every truss, or do I have to give you something else?
I think that's it.
You think that's it? Okay. So let's see if that's right. So what I want is to find the forces on each of this truss, and each truss in this structure. But I'm going to give you some hints. Let's say I look at a truss individually, a truss DC, just DC individually. I have my truss, I have my two hinges, and the truss will experience either a compressive force or a tension force. And we're looking at this rigid body, right? We're looking at a rigid body right now. Now, of course, this is a two-force member because this truss will only experience forces at each of these 2 points. And what did we say about two-force members? Remember, two-force members will always have the force with the same magnitude, but in the opposite direction. So in other words, if we find out from this hinge that this truss is experiencing a force, a compressive force in this direction, then on the other side, it also has to experience a compressive force in the opposite direction in order for there to be balance here, okay? So that's one of the first things I want you to know about trusses. They experience the same force on each side, just acting in the opposite direction. So either a tension force or a compressive force. The second thing I want you to know before we start this analysis is that we're going to look at hinges, and if we're looking at hinges, at these hinges or these joints, then we are essentially studying particles because we can reduce those joints, instead of looking at them as a circular element, we can reduce it to a simple particle. But don't be confused. When we look at joints and when we look at trusses, the same forces will look like they have different directions. For example, let's say we're looking at one joint, just the joint, and the truss is experiencing a tensile force. Does the joint feel that it is being pulled at or pushed into if it's a tensile force? Not both. Let's just look at just one joint, look at one truss, just that one force. We're not trying to find balance here or anything. Right now we're looking at a joint. There is a truss connected to it, but we're not studying the truss. We're studying the joint. So right now, if the truss feels tensile force, if the truss feels that it's being, you know what tension is, right? Tension? Okay. So the truss feels tension. What is the joint feeling? Is the joint feeling a force into it or out of it?
Out of it.
Out of it, right? So when we're studying the joints, our force will be pointing out of the joint. Okay? However, if we're studying the truss, so instead of looking at a particle, if we're studying the rigid element that is the truss, and the truss is experiencing tension, in which direction would you draw the force?
Inwards.
Outwards if you're studying the truss, right? So, like I said, we're looking at two different things. The joint individually will be outwards, but then if you look at the truss individually, let's say I hold the two ends of the truss and I want the truss to be, to experience tension. What am I going to do? Am I going to push in or pull out?
Pull out.
Okay, so the truss is going to be experiencing a force in the opposite direction. So this will be a little bit confusing because these are the same force, but when we draw them, we're drawing them in the opposite direction. So you might think, wait a minute, that doesn't really make sense because it's the same force. So what do you think is happening here? Here, we're looking at equilibrium now. if this is a static system, then the force that the joint is feeling should cancel out with the force that the truss is feeling. That's why, even though they're the same force, they're acting in opposite directions. So don't be confused. When we say tension, whatever it is you're studying, it'll always be outwards. When we say compression, whatever it is you're studying, it'll always be inwards. Even if when you combine them, they look like they're in different directions. Now, for simplicity, I will say in most, if not all, actually in all of our truss problems, just for simplicity, we're going to study joints instead of the trusses because it's easier to study the joints. Okay? So for now, don't worry about mixing up the joint and bodies, the joint and truss studies. We're going to focus on the joints, and we're going to use what we learned from the joints in order to draw conclusions about the truss. So when we draw free body diagrams, we're going to draw free body diagrams around joints, which we will treat as particles. So you don't have to worry too much right now about rigid bodies. So let's go ahead and try to solve this problem. We have a force of 450 pounds acting on the system. Now, of course, we've already said that the system really can't move. Other than rotating about point C, all of them together, there is no relative motion, which means that if I'm applying this force and these are rigid bodies, they cannot move. Okay? Right? Because this will try to flatten this, but then these three will actually hold it in place. So if this is not moving, then this is a static system, right? Good. And because it's a static system, then my sum of forces in the x direction equal?
0.
And in the y direction?
0.
And in the z direction?
0.
And the moments?
0.
Okay. So today, we're not going to focus on the z direction because this is a two-dimensional structure. And we'll notice that for now, right? For now, when we look at moments, we're going to have to select a point. Now, it was easy when we're dealing with rigid bodies. We looked at the point where there were more forces acting on it and then just use that. But now things aren't really that easy because we have multiple points through which we can calculate a moment. And it's really up to you, the engineer, to find that best point. Okay? Or the physicist. Okay? So it's really up to you to find that best point. So, we have the system. We have these equations, and we know that they will be true for anything we study. They'll be true for the trusses, they'll be true for the joints, they'll be true for their supports. Where do we start?
At the joint, the forces.
Okay, that's true. We can start at joint D. Why? Well, we already have a value. If we start at B, we have just 3 unknowns, so we can't really do anything with that. But if we start at D, we already have at least 1 known value. Now, that may not help us too much, but at least we can start there and get some sort of relationship. Okay? So I'm going to start at D. And I'm going to draw a free body diagram of all my forces acting on the joint at D. On the joint. So what forces do I have?
For starters, the external force.
Okay. We have a 450-pound force acting on the joint. That's right. What else do you think we have? Exactly, right? So we have a 450-pound force, and then these trusses will experience either tension or compression. What that means is that they will exert a force either out of or into this joint. Now, there are different conventions on how to draw these initial forces. Of course, you can find out these forces conceptually just looking at it. I mean, you just said, this force will be a tension force. It makes sense, right? You're pushing this joint away from it, it'll be tension. But let's say that it's not that intuitive, right? Let's just say for our purpose that it's not intuitive. The convention that we'll use here is the convention that most textbooks use, is to always assume an outwards or a tensile force, okay? So convention is to always assume an outward or tensile force. And what does that mean? Remember I mentioned that it doesn't really matter in which direction you assume your force. If you assumed correctly, how will you know in the end?
It's a positive answer.
If you assumed incorrectly, how do you know in the end?
It's negative.
Exactly. So we're going to assume a tensile force, and that way any force that I get positive will be a tensile force, and any force that I get negative will be a compressive force. That's the convention, okay? So if we assume always an outward or tensile force, then every force that's positive will be a tension or tensile force, and every force that we get negative will be a compressive or compression force. That's it. That's the convention. You don't have to, each one of you, follow this convention. But it will help organize our, well, not our, my grading. Okay? So you don't have to, but if you don't want to follow this convention, then remember, you have to make sure that you identify the force as a tension or compression force. Okay? Now, for our purposes, I'm just going to do both. I'm going to use this convention and in addition, identify the force. But really, you only have to do one if you don't do the other. Okay? So, I'm going to assume that my forces are all tensile, even though I know that not all of them will be. So I have a force from C to D. I have a force from B to D. And I have a force from A to D. Just convention, not necessary, but I just try to write these alphabetically so I don't get confused. Because sometimes I write C to D, then I write D to C, but I forget that they're actually the same value, right? Because tensions are two force members. So just my own personal convention is to write these in alphabetical order, but you don't have to follow that, okay? Good. How many unknowns here?
3.
Ooh, how many equations do we have to solve?
3.
Not really, because we can't do anything with moment, because we're looking at a particle, not a rigid body. So 2 equations. We may not be able to solve this one. But let's try anyway. Let's see what we can get. If I start with my sum of forces in the x direction, we know that equals 0. What forces do I have in the x direction right now? Negative 450. What else? Negative 450 pounds, right? What else do we have in the x direction?
We don't know yet because we don't have an angle or a substitute for FAD and FA or FCD.
But we can find an angle.
So that's why I said we don't know yet.
Okay, so let's write these forces as simplified as we can. So let's write everything in terms of one of these 3 forces. So FAD, okay, but in the x direction, what do we have?
Force AD cosine 45,
That's correct.
and that means minus that.
That is correct. How do you know it's cosine of 45, Noah?
When not hypotenuse, the opposite and adjacent are both equal, it's a 45-degree triangle.
That's correct. If
When it's a right triangle.
Yeah. If that answer that Noah gave is not satisfactory enough for you, then just remember, inverse tangent of y over x. Inverse tangent of 1 is 45. So again, both the opposite and adjacent sides are the same, then the angle is 45. So we get FA minus FAD times cosine of 45, good. What else do we have? Times what? What about FBD? Okay, so all this equals? Good. Ugh, 1 equation, 2 unknowns. Not much we can do there. Let's move on. Sum of forces in the y direction. What do we have? Like this? There we go.
FAD sine of 45. It'll be also negative. And then FCD sine of 45 is also
Now this equals 0. Ugh. 3 unknowns, 1 equation. Total 3 unknowns, 2 equations. We cannot really solve this. What now? What's next? What do you think we can do next? Next joint. That's true. We can't solve one joint. That's okay. Let's go to the next one. And the next one, until we can figure out what we can solve. Now, because we started directly with a problem, I do want to check in. Is everything making sense to you so far, or are there any questions, Jared?
No good.
What about you, Noah?
Only when coming to the next step of the problem. So right now we've just been looking at the joints, but will we also be looking at the individual beams?
Not for this week.
Okay.
So this week we're going to focus on particles, on joints, just for simplicity.
Okay.
Graham?
Why is there no angle on FBD?
Here? Because it's acting in the y direction.
Oh, I see.
Yeah, there's no component, it's the whole thing. Yes?
Following from Noah's question, does that apply also for the exam that we're only looking at the particles?
Yes. I feel like I should know your name, right? Ryan. Any questions? Tuong? Jenny? Good. Kevin? Daniel? Luis? Nice. Got all your names. Good. Except Ryan's. So, like I said, or like one of you said, if we can't figure it out, then let's move on. We can move on to the next truss. Which one do you want to go to now?
A.
Do you really want A?
No, C.
Do you really want C?
Yes.
B, that's a good one. Yeah, good choice. Let's move on to truss B. And we'll see why in just a second. You'll see why I want to move to B in just a second. So we get B. I have my X and my Y axes. And then what forces do I see acting on B? Remember, by convention, let's assume that they're all tensile forces, even though they may not all be. But what forces do we have? Force AB. Force AC. Force BC. There we go. And then force. Before I even start writing equations and solving them, can anybody figure out what this is telling us just by looking at it? Okay, FAB and FDC are equal. That's true because of equilibrium in the x-axis. What else is this telling us? FBD is 0. Do you see that? If you don't see it, it's okay. We will through the math. But I want to see if you could see it at least conceptually. Let's do the math. Sum of forces in the x direction equals 0. And in the x direction, I get negative FAB. And of course, it's already in the x direction, so no components. Plus FBC equals what?
0.
Okay, so I get that FAB equals FBC. And then I get that sum of forces in the y direction equals 0. And what does this tell me? What forces do I have in the y direction, Noah?
Force BD.
Okay, and what other force do I have in the y direction?
That's it.
That's it. So FBD equals? Look at this. FBD equals 0. How does this help simplify our problem?
You can take that value and plug it back into joint D.
So we see FBD equals 0. So now, how many unknowns do I have here?
2.
How many equations?
2.
And now can I solve this? Yeah. So sometimes it's not, you're not going to solve everything just on the first try. You're going to have to go through the different joints and then figure out relationships from the different joints, apply them into your original joints, and then solve for them. Now, why is this possible? Because my joints are two force members, and because they're two force members, my trusses are two force members, and because they're two force members, the forces at one end have to be equal to the forces on the other end. So if the force here at this end of the truss is 0, the force at this end of the truss has to be 0, which means that this FBD equals 0. And now I can solve it. Now, you may not like this because this will involve us going back and forth between our systems. Because, yeah, I mean, we're going back to our joint D. But if you want to make my life easier, keep all your joints together in one place. So try to write joint D, maybe leave some space in case you have to go back to it, okay? Just make my life a little bit easier. So we get D. So unfortunately, this direction equals FAD, FAC. Okay, we can find some function there. And then we have FAD, FCD. I'm going to deal with this one. I would like to work with this f of y equation. Why? Because this f of y equation, what does this tell me? This equation tells me that FCD sine 45 equals negative FAD sine 45. And now what do I get from here?
FCD.
I can cancel my sine of 45. What else?
FCD equals negative FAD.
Ah, so FCD and FAD are actually going to have the same magnitude, but they'll be in different directions. And that's good. That's good. That's good. So now that we have that relationship between FCD and FAD, can I plug it back into my x direction equation and find that? Yes, I can. So I get, and I don't have much space on the board here, so I'm going to try my best to keep it organized. But I get this relationship, and then going back to my x equation, I get from my x equation that negative 450 pounds minus FAD cosine of 45 plus FCD cosine of 45 equals 0. But of course we said that FCD is negative FAD. So if I had negative FAD, I can simply replace it with positive FCD. And now can I solve for this? Can anybody give me that number?
$636.4 pounds.
Can somebody confirm that value?
Yeah.
Half of that. Okay, so what, 318? Was this a positive or negative number that you got?
Which one? CD?
Like what you just calculated, yeah.
Positive.
Okay, so does that mean that we chose the right direction? Yes. Which means that FCD is a force in tension. Got a positive value, so FCD is in tension. So we get that the force on this joint is 318 pounds in tension. Okay? You good? 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 And now we know that FCD is negative FAD. So if I want to solve for FAD, and again, I want to keep it organized, but we don't have that much space. I get that FAD is negative FCD, or simply negative 318 pounds. And what does this negative tell me, Ryan? It's a compression force, right? Compressive force. Which means that this force, FAD, is equal to 318 pounds in compression. Again, if you use this sign convention, then positive or negative is enough. If not, you can always use tension or compression. If you feel like you want to make my life even easier than you already do, then just write both. But either should be fine. Good. So look at that. We found 1, 2, 3 forces. in 3 trusses. Just by looking at 2 joints. So not bad. We looked at 2 joints, we found 3 forces. What's next? Okay. You said C? Okay. So let's look at that. I'm not sure if you like it when there's multiple ways to solve something, but I do. And in this case, we'll see that there's actually multiple ways to solve this. I mean, we can start in a different order. But let's go with C. If I draw my free body diagram on C, what forces do I have?
FCD and BCD. Sorry, FBC.
Okay, so FCD in this direction, right? Okay. Is it in this direction?
No.
Okay. There we go. 1, we know it's tension, but 2, just by convention, right? We will set it as a tensile force. And then we have FBC, right? Now, from what you know from statics, are these the only 2 forces?
No.
What are we missing?
The normal forces too.
There we go. We have a hinge, right? Remember that hinges, right, exert a force. So we will have a force from the hinge. I'm just going to call it Cy. And a force from the hinge, I'm just going to call it Cx. Now, because these are not these tensile or compressive forces, these are simply reactions, you can set your direction however you see fit. Okay? In fact, I'm going to set this one in the other direction, just to make my life a little bit easier. Okay, you set your direction however you see fit, because these are not tensile or compressive forces in a truss. These are reaction forces. Okay? Sorry? Not yet. We haven't really started covering friction in statics, but because the hinge is not moving, there cannot be any friction because it isn't moving. Okay? So no friction, but not yet. We will look at friction later. Good. Okay. So what equations can I have? Well, I have my sum of forces in the x direction.
Sir.
Yes, go ahead. Did you just call me sir?
Mister.
You're not making it better. You're making it worse.
Oh man, wouldn't the CY be on the opposite direction because it's a reaction?
Yeah, we can do that. Good job, Sofia Gomez Yataman Molejo. All right? I'm not kidding. That is her last name. So, what do we have in the x direction? Graham.
Is it the force in the x direction?
Yeah, which forces do we have in the x direction?
FBC minus FCX equals 0. Or, no, sorry, plus.
There we go. Okay?
Okay.
Are those the only forces we have in the x direction? What am I missing?
There's
Need
FCD.
the cosine of the CD force.
Exactly. Minus FCD times cosine of what? 45 degrees. That's correct. Now this equals? 0. Do we know one of these forces? What do we know?
Or CD,
And what is FCD equal to?
318
Positive or negative?
positive.
Positive. Okay, so I get that minus FBC plus CX minus 318 cosine of 45 equals 0. How many unknowns? Okay, we still can't solve it yet, but we're getting there. That's good. Sum of forces in the y direction equals 0. And what forces do I have in the y direction?
The sine of the CD
Okay, so I get that FCD
and the
sine of 45
CY
plus or minus?
minus
Minus CY equals 0. Do we know any of these variables?
you know the CD.
FCD, right? Okay, so FCD is 318 sine of 45 minus CY equals 0. How many unknowns? Can I solve it?
Yes.
Okay, so CY is equal to what? 318 sine of 45. And what's that?
4.9.
Units?
Pounds.
There we go. Good. We found a reaction force. Remember, reaction forces, I'm going to round it up to 3 significant units. Remember that our reaction forces aren't tensile or compressive forces. They are simply reactions from your supports. Okay? But we still have 2 unknowns here. So we still need more information. So what's our next step?
Plug CY. Oh wait, no highlight. Never mind.
Yeah. So what's next? Okay, move on, right? Let's look at the next joint. Now, before I look at the next joint, I do want to remind you that even though we're looking at this system as if they were just particles, we can still see the system as a structure, right? As an individual structure. Okay? So I am going to switch to the A joint and then figure out what relationships we can get there. But remember that we can also look at this as a structure, right? As one system. And why am I saying this? Because if we can look at this as one system, in other words, if we were to pretend that these trusses are all rigid bodies that are connected through fixed supports, then I can still find those reactions before looking at the individual joints. Okay? But let's talk about that after we look at joint A. Okay? I notice some faces are like, wait a minute, what? Okay, so let's just look at the joints first, and then we'll look at the system as a whole. Okay, joint A. Sophia, what forces do I have at joint A?
Force FAB,
Okay.
and then force FAD, the reaction forces to the X and to the Y.
Why X?
It's on a roller, right?
It's on a roller, right?
It's only
Oh,
on
yeah.
the surface.
So just a Y reaction force. Okay? Not bad. Remember, for convention, we're going to set these as tensile forces, but just looking at the system, you know that one of these has to be negative, right? Sorry?
It's AY.
Oh, thank you. Wow, you're on a roll here. You went from saying all these bad, lame jokes last week to actually participating this week. Good job. I'm going to give you a chance to continue that roll. We have small forces in the X direction. What are those forces?
Is FAB,
Mm-hmm.
and then the FAD cos
Yep.
5.
Yep. All this equals?
0.
Good. Do we know any of these two variables?
Yeah.
Which one?
FA.
FAD, right? Okay. So I get that FAB plus, what was FAD equal to? Negative 318. Okay, so minus 318 pounds times cosine of 45 equals 0. And that gives me that FAB equals what?
229 pounds.
Sorry?
229 pounds. That's it, yes.
Can somebody confirm this value?
Wait, 24. Is that 20? CY, is that 24 or is that 29? 225.
225.
Oops,
Somebody confirm. I mean, it should be, right? Because 318 sine 45, 318 cosine 45. But just in case, can somebody confirm that?
I'm pretty sure that's a negative value too.
Why? Remember, FAD was negative. When we move it to the other side, it's positive, right?
How do you get negative 318?
Because we're setting our convention to be positive in tension and negative in compression. So when we first calculated FAD, we mentioned that FAD was negative of FCD. So FCD was 318, FAD has to be negative. And the only thing that negative means is that it's not a tensile force, it's a compressive force. That's all it means, okay? So we found FAB. Can we now find the forces in the y direction? I'm going to say yes. What forces do we have in the y direction?
And y
Okay, what else?
plus FAB sin
Mm-hmm. That is absolutely right. And then again, do we have one of these two variables? Jared?
Yes, FAD.
Exactly. So we get that FAY plus FAD is negative 318 sine of 45 equals 0. And AY equals how much? I don't think we need to use our calculators, right? 225 pounds. So I'm going to write it down here. FAB is 225 pounds in tension or compression? Okay. And then we get that the reaction force in the y direction is also 225 pounds and then upwards. Ooh, it looks like we're starting to solve our system. I think it's starting to all make sense. We have one truss left, and then we have one X reaction left. So do you think we have everything we need to solve this? Okay, so what's the next logical step? Where do we move back to?
Take it back to B.
Exactly. We go to B. Why? Because we already have this relationship. FAB equals FBC. We already found that FAB is 225 pounds, right? So what is FBC equal to? 225 pounds. And is that in tension or compression? And now, what's the final step? Where do we go to now?
The reaction force on C.
Okay. And on C, we had that minus FBC plus CX equals 318.45. But now we know FBC, right? What was FBC equal to? 225 pounds. We get a negative 225 pounds plus CX minus 318 cosine 45 equals 0. So what is CX? I'm just going to write it down here. What is CX equal to? Move it to their side. You get 318 cosine 45. Move it to the side, so you get plus 225. So how much is that?
450 pounds.
450 pounds. Now before I move on, are there any questions? It's very important that if you have questions that you ask them. Yes, go ahead.
Can you explain why you chose the order you chose for the free body diagrams?
Well, this one I just asked, and one of our students said this one, and so I'm okay with that. I think it's a good place to start because you always know, you have one value that you know. That's the only reason I would start with. I went with this one because there are three forces, and because of the nature of this diagram, we can be clear that this has to be 0 because there's no other y force. Everything else I just asked and someone said, and I just followed. It doesn't really matter. If it's easier for you to just start left to right and then just start moving back and forth, that's also fine. But essentially, when we're dealing with a truss system, we're not going to be able to solve everything on the first try. Notice that for each and every one of these, we ended up with some unknowns that we have to go back to, right? So it doesn't really matter which ones you choose as long as you cover all of them. Yes?
Is there a clear way you would want us to be labeling, like when we're moving back and forth? Or does that not really matter?
I feel like that'd be a little bit too much to worry about right now.
Okay.
Right now, I would worry about getting the procedure right. Okay. And after that, you can worry about labeling. But for now, I think all of your D's, keep them in one place, all of your B's in one place, all of your C's in one place, and all of your A's in one place for now. Okay? I just don't like saying, well, D for this, then B, then back to D, whatever. I prefer that all the joints are in one place so we can look at them together. But don't worry too much about how I will evaluate your work, even though that's what you should be worrying about. Worry about your understanding of it first, okay? Any other questions? I have more of a conceptual thing, just from statics. Does it make sense that this C is actually the same magnitude as this force, but in the opposite direction?
It does.
Why?
It's the only reactionary force in the x direction.
Exactly. So remember when I mentioned earlier to look at these not just as individual bodies within a structure, but to look at it as one structure, because we can actually find these reaction forces before having to go through this process. Now, notice that it's not necessary because we found them anyway, but it's still possible. And I'll leave the decision up to you on whether you want to find the reactions first or look at the joints first. So what I'm going to do is I would like for us to look at this system as if it were one individual structure. So don't look at the trusses individually. Look at the structure as a whole. So I have a hinge here, and I have a roller here. This is my system, right? And I'm applying a force of 450 pounds. Looking at the system as a whole, right? I can say that the sum of forces in the x direction equals 0. And if I take equilibrium about this rigid body as a whole, what forces do I have in the x direction? I have negative 450 pounds. And what other force is acting in the x direction here?
The reactionary force.
The reaction from the hinge, right? So plus Cx equals 0. And this tells me that Cx equals 450 pounds. Does this make sense? Do you understand how it makes sense? Daniel? Luis? Good? And now, notice another thing. I don't have any y force, but I do have two y reactions. And how do I find them? Well, I can take my sum of moments about my point C. And if I look at point C, which forces are causing a moment? We have this 450 pound force acting at a distance of 4 feet. So if you take the perpendicular distance to the line of action of the force, that's 4 feet. And it's a counterclockwise moment, so it's a positive moment. But then what else is causing a moment? There has to be something holding it in place.
The reaction from the roller.
Exactly, the reaction from the roller. So I get minus AY times the distance between the hinge and the reaction, that's 8 feet, and all this equals 0. And what this tells me is that AY equals 450 times 4 over 8, or just half of 450. And what's half of 450? 225. 225. And now I can go to my sum of forces in the, I don't want to erase this, it looks pretty. I can go to my sum of forces in the y direction, and I get in the y direction, I have an AY, and I have a CY, and that equals 0. So CY actually equals AY. So CY will be equal to 225 pounds. And what did we get? 225 pounds. Okay? Any questions? So you can either do all this, it's fine. You may want to find your reactions first, and then you have less unknowns here. That's also fine. Regardless of what method you choose, you're going to arrive at the correct answer, just like we did here. Ooh. Is it time to go? Now we are more than 15 minutes left. Okay. I feel like we covered a lot in just one problem. Don't you feel so? I feel like we did a lot of material. But I like this problem because it does allow us to see this whole joints method and then looking at it as a rigid body. Now, there are different methods of analyzing trusses. The one that we just did is called the method of joints because we study individual joints. Okay? Now, next time we meet, we're going to study the method of sections because we're going to study sections of my system. And of course, you already know equilibrium on a rigid body, which is what we just did here and what we covered last week. So, like I said, it's the same material. We're just adding a little bit, maybe combining it with the previous material. But notice that this is just chapter 3 in action, and this is just chapter 5 in action. And these moments are chapter 4 in action. Okay, so We have the same material. We're just starting to combine it and add a little bit to it. Now, I need to be absolutely sure that you understand this because this will be on next week's exam. So I know some of you may find this annoying, but I will do it anyway. Jared, are there any questions?
Doing great, sir.
Graham?
Yes, sir.
Noah?
I'm good.
Ryan?
I'll get it.
Tuong?
I'm good.
Luis?
Good.
Daniel?
Good.
Sophia? Kevin?
Good.
Jenny?
Yeah, can you explain this reaction and action thing again in the arrow direction? Like whether or not it's acting, what did you say, tensile or compressive?
Yeah. So these trusses are rigid bodies, right? Now, the way the trusses are arranged, their connections, their joints are taken to be like pins or hinges, right? Which means that they can freely rotate about the hinge or pin, but they cannot move in linearly, okay? So what that means is that the joints will only experience either tension or compression. So those are the only two possible forces that these trusses can experience, okay? So that's one thing. Now, because those are the only two possible forces, we express tension as moving out of your body. So in this case, if this force were really in this direction, moving out of the particle, it's a tensile force. And if it makes you understand a little bit better, I would like to always look at this force and picture myself pulling on this joint, on this truss, right? If I'm pulling out of it, right, the force is out, then I'm exerting a tensile force. So that's tension, right? Pull is tension. So from convention, right, because we don't want to confuse ourselves with all these different forces acting in different directions, we say that a force is positive if it's in tension. So if you're pulling, it's a positive force. And we say that a force is negative if it's in compression. So if you're pushing, it's a negative force. And that's just for convention. That's just to help us not get lost within all these equations. So if positive is tension, negative is compression, the only way you can get a negative value in your equation is if you assume your direction incorrectly. So what we'll do is that we will always assume that my force pulls. So my force is out of my particle, so it's always tension. And if we assumed correctly, my answer will be positive, so it's tension. If we assumed incorrectly, like FAD, if we assumed incorrectly, my answer will be negative, which means it's compression, pushing. That's all it is. You don't have to do it this way. It's just easier to have a standard convention so that we don't get lost in our barrage of equations. Okay? Hopefully that answers your question. If not, I can.
Yeah.
Okay.
So we were saying at the beginning, because there's no translational motion,
Mm-hmm.
that's the reason why only tension or compression could act on it.
Mm-hmm. So not just because there's no translational motion, but because these are rigid bodies, there's no shear motion, which means that this is a rigid body, its shape cannot change. So because its shape cannot change, you cannot bend it. So if you cannot bend it, there's no shear force, there's only normal force. So only tension or compression.
Okay.
Yeah, that's just part of the definition of a rigid body.
But in practice,
Mm-hmm.
they're not actually rigid.
That's correct.
Okay.
And you'll see that in a class called Strength of Materials, right? So in practice, our bodies are not all rigid, and then we'll deal with more equations for non-rigid bodies. That's correct.
Okay.
When working on the studying overall for the test, will the problems look more like the fundamental problems and the type of problems we did here in class, or will they be more complex like the homework problems?
I guess it depends on how much I like you. No, I'm kidding. They will be homework problems, right? So you should be prepared to answer the hardest of your homework problems as well as the easiest of them.
Okay.
Right? It can be any one of them. And it'll be random, but I will definitely make sure that everybody gets the same level of difficulty. So I'm not going to give you all the easy ones and then Jared all the hard questions. Like it's random, but I have a say in what I choose, right?
Gotcha.
To make sure that everybody gets the same level of difficulty.
So in the same vein as problems that we've already solved, if we've done all of them.
Yeah.
Is that what you're saying? Okay.
Yeah.
What Can you go over again what resources we'll have?
Your homework.
Okay, so we can print off all of our homework and bring that with us?
Yes. I mean, not bring it. You'll be wherever you want to be, but you're
Oh, right.
not. We're not going to be here.
Gotcha.
Oh, so is it all gonna be online?
We're gonna have class next week?
No. We'll have a review session on Thursday. You don't have to attend since you're an in-person student, but if online students will still have a review session on Thursday.
What time so on Thursday?
8. It's from 8 to 8:30.
8 to 8:30.
Yeah. So next week the scheduled topic is internal forces, if I remember correctly. That's very easy. We can cover it in a 30-minute review session. Okay. And then if we need to take some time of the following week, that's also fine. We're well ahead of schedule right now. So most courses start this topic on week number 10, right? And we are at week number 8. So we're already 2 weeks ahead of most of the other sections that teach statics. Oh, I think we're good. Okay. Any other questions? Okay, if there are no other questions, I will let you go. And I will let myself go, because I want to go home as well. Have a good week.